Hi everybody, today we're going to talk about inverse trig functions. Specifically, we're going to look at definitions with stricter domains and we're going to find a few values of inverse functions. We are going to restrict our discussion today to just sine x, cosine x, and tangent x. So let's start with this scenario of why would we do this? Let's say we wanted to figure out what angle we would want to put a camera to reach a certain spot. It might help to bring in a triangle. We know the height we want the camera to be. We also know the spot where we want the camera to aim. What we are trying to do is to find an angle that corresponds to a ratio. To find the angle, we need to bring in inverse functions. Let me remind you a few things about inverse functions. If the point xy is on the graph of a function, then the point yx is on the graph of the inverse function. Only one-to-one functions have inverses. We can use the horizontal line test to determine if a function is one-to-one. As a helpful note, I thought we should talk about notation. We write inverse functions using a -1. F with a -1 of x is the inverse of f. This -1 is not really an exponent, so f inverse of x is not equal to 1 over f of x. As a trig function, sine inverse of x will not be equal to 1 over sine x. Remember, 1 over sine x is cosecant, and cosecant and sine are not inverse functions, they're reciprocal functions. Take a look at the graph of sine x. Is this a one-to-one function? Using a horizontal line test, we can see that the answer is no. I can see multiple points where the horizontal line crosses the sine function. What if we restrict sine to just one full period of sine? This graph looks at sine x over 0 to 2 pi. Once again, if I put in a horizontal line, we can see the horizontal line crosses the graph at more than one point. Sine of x is a one-to-one function over the interval -pi/2 to +pi/2. To get the graph of the inverse function, I'm going to start with the points on sine x. I have -pi/2 with -1, 0, 0, and pi/2, 1. I'm going to flip each of those points around. -pi/2, -1 becomes -1, -pi/2. 0, 0 is going to stay the same. Then pi/2, 1 becomes 1 pi/2. We can graph those 3 points on the same graph as sine of x, and then graph sine inverse. Notice the graphs are not opposite, but they're symmetric to the line y equals x. When we look at the inverse sine function, y is equal to the sine inverse of x if and only if x is equal to sine y. X will be between -1 and 1, and y will be between -pi/2 and pi/2. This says we can only take the inverse of a ratio between -1 and 1, and all of our answers will come out between -pi/2 and pi/2. Let's try a few examples. Let's find the sine inverse of -1/2, and for reference, we'll call that theta. Sine inverse of -1/2 equals theta means that the sine of theta will be equal to -1/2. Think back to your angles. You want to think about when is sine of theta equal to -1/2, and hopefully you're remembering that that would be at -pi/6. Let's solve sine inverse of the square root of 2 over 2 equals theta. I'll start by saying sine theta would be the square root of 2 over 2, which hopefully you remember means that theta would be equal to pi/4. Oftentimes we may need to use our calculators to find our inverse functions. If I look at the sine inverse of 1/4, it doesn't fall into the angles we look at when we look at a unit circle. We're going to use our calculator to find the answer. We're going to answer in radians, and we will round to 2 decimal places. On a handheld calculator, sine inverse is usually located right above sine on your buttons. So I'm going to hit sine inverse of 1 divided by 4, and I get 0.25. You may want to check your mode before you get started doing these calculations. Let's find sine inverse of -2 divided by 5. This time I got -0.41. Now we're ready to take a look at cosine. Cosine of x is not a one-to-one function. Again, I can put in a horizontal line and see that it passes through cosine at multiple points. So what interval should we use to restrict the domain? If we restrict our domain from 0 to pi, we have a one-to-one function. Let's again draw the inverse function. We'll start by putting in our points for cosine and then reverse them to find the points on cosine inverse. I can see I have the point 0, 1, which flips to 1, 0. I have the point pi/2, 0, that'll flip to 0 pi/2. And I have the point pi -1, which flips to -1 pi. We'll start with our graph of cosine of x. We'll add our inverse points. and we can connect the dots. To see the symmetry, I added the line y equals x. Cosine inverse of x is equal to y if and only if x equals cosine y. X again will be between -1 and 1, but y will go from 0 to pi. Let's try finding the exact value of cosine inverse of -1 equals theta. We can rewrite this as cosine of theta equals -1, which tells us that theta will be pi. Let's find the cosine inverse of 1/2 equals theta. This says cosine theta is equal to 1/2. This tells us that theta is pi over 3. Our last trig function is tan x. What interval should we restrict tan x in order to make it 1 to 1? We can see that we have a full period of tan x from -pi/2 to pi/2. Notice this is an open interval. Tan x is not defined at the endpoints. We want to be careful on how we write our intervals and if we include the endpoints or if we don't. We will write that y equals tan inverse of x if and only if x equals tangent of y. This time x is from -infinity to infinity. Y is from -pi/2 to +pi/2. Let's find the exact value of tan inverse of the square root of 3. Tangent is equal to square root of 3 at pi/6. Our second one says tan inverse of -1. If we think about it, we remember that tangent is equal to -1 at -pi/4. We will do a lot more problems in coming videos. What I want you to take from this introduction is the restricted domain that goes with each inverse function.